Hello everyone, my name is Khalid Sarag. I'm a PhD student at Purdue University. Today, I'll be presenting our paper, Evading Voltage-Based Intrusion Detection on Automotive CAN. This work has been done in collaboration by people from Purdue University, EPFL, and IIT Delhi. With the ever-expanding number of microcontrollers on vehicles, modern vehicles are frequently called computers on wheels. These numerous microcontrollers, such as the telematics control unit, the infotainment unit, and the vehicle communications interface module, while providing increased functionality and control, they also increase physical and remote attack surfaces of the vehicle. Security research has repeatedly shown these different attack surfaces to be vulnerable, allowing an adversary to control one or more microcontrollers in the vehicle. This has led to the development of novel CAN-specific intrusion detection systems that are based on message anomalies and physical features of microcontrollers, such as voltage levels and clock skews. These IDSs are dominant on CAN bus as they do not burden the resource-constrained ECUs with non-trivial computation and communication overhead. While message-based IDSs and clock-based IDSs have been susceptible to attackers, voltage-based intrusion detection systems, or VIDS, have proven highly effective and popular in detecting masquerade attacks. We look at the design common to all existing VIDS. While the VIDS is operating, it measures the bus voltage during message transmission at a certain sampling frequency. Then it classifies the ECU voltage fingerprints. However, since the voltage fingerprint of an ECU fluctuates over time due to aging, environmental factors, and ECU reconfiguration, the VIDS needs to frequently transition to the retraining mode and to relearn a supervised model of the ECU voltage fingerprints. We know that there are two challenges for the attacker trying to evade VIDS. One, that it's difficult to controllably alter hardware characteristics and hence the voltage fingerprint. And second, that various VIDS protect against training set poisoning by securing the retraining modes using state-of-the-art countermeasures such as message authentication codes. We present Duet, an accomplice-assisted masquerade attack that addresses these challenges. Duet involves a duo of attacker and accomplice that carry out a training set poisoning attack in a stealthy two-staged fashion. Duet utilizes a novel voltage corruption tactic, which corrupts voltage features on the bus by transmitting an attack message simultaneously with a victim message. Duet is a two-stage attack. The first stage is the voltage fingerprint manipulation. It is carried out during the retraining modes of the VIDS. Here, Duet manipulates the VIDS into learning a distorted fingerprint of the victim as the victim plus the attacker. The second stage is the fingerprint impersonation stage, which takes place during the operational mode. Here, the attacker impersonates the distorted fingerprint by sending simultaneously with an accomplice. Voltage intrusion detection systems will classify the distorted attacker plus accomplice fingerprint as that of the victim during the operational mode. We note that Duet utilizes deficiencies in the CAN protocol, real-world hardware capabilities, and common characteristics of CAN controllers. It is not specific to any ECUs, vehicles, VIDS features, or classification models, and it is effective against secure retrainings. Further, we present RAID, a lightweight orthogonal randomization defense to defend against Duet and to be used along with other IDSs. We start with a background on CAN communication. CAN represents bits using differential voltage signaling between two wires, with 0 being dominant and 1 being recessive. When two ECUs try to transmit a dominant and recessive bit simultaneously, the dominant bit prevails. We also know that most of CAN functionality is implemented in the hardware, and the application software can only set the identifier and the data. Hence, a malicious ECU with a compromised application software cannot alter the ECU's voltage characteristics. CAN messages are transmitted in two formats: the standard frame format with an 11-bit identifier and the extended frame format with a 29-bit identifier. This is followed by the control, data, and other fields. If the controller encounters an error in the transmitted signal, it increases its transmission error counter, or TEC, by 8. The TEC is responsible for maintaining the node state. A value of 128 or higher makes the node error passive. A value of 256 or higher disables the node and puts it in the bus off state. The node then must be reset to restart communication. On observing an error, the CAN controller transmits an error frame. Error frames are composed of a flag and a delimiter. Error active nodes send active error frames with a 6-bit dominant flag, while error passive nodes send error passive frames with 6-bit recessive flags. This means that active error frames interrupt ongoing transmissions, while passive errors do not. In fact, passive error frames are undetectable on the bus as their voltage level is the same as the idle bus voltage level. With this background, we present our attack Duet. Duet is a two-stage attack that utilizes a voltage corruption tactic to impersonate a victim. First, Duet manipulates the voltage fingerprint of a victim during the VIDS retraining mode, and then later impersonates the victim during the operation mode of the VIDS. The voltage corruption tactic, which allows an ECU in the error passive state to corrupt the voltage features of messages of another ECU, is carried out by first transitioning the attacker ECU to the error passive state. Next, the attacker transmits simultaneously with the targeted ECU without raising detectable active error frames. Finally, by preventing the retransmission of the attack message. For executing the first step, it is not possible to change the error state through software. Hence, we utilize simultaneous transmission to have the accomplice transmit simultaneously with the attacker and induce errors. We repeat this until the attacker reaches the error passive state. In step 2, for the error passive attacker to transmit simultaneously with the victim, it must use a preceded ID to counteract inherent jitter in victim's messages and its own inability to control message transmission time. However, as the error passive attacker has an 8-bit suspend transmission period for consecutive messages, an accomplice is required to insert preceded IDs for simultaneous transmission. A common characteristic of CAN traffic is that certain portions of message payloads are predictable. In this step, the error passive attacker uses this characteristic to send a message whose content overlaps with the victim's message until a desired bit location. As a result, we find that the voltage features of the victim ECU have been distorted as a combination of corrupted and non-corrupted voltage values. This can be used to manipulate the VIDS. Finally, the attacker must be prevented from retransmitting the attack message, as it will likely raise a VIDS anomaly. This is easily done by one of two options, either canceling transmission on error or by using a one-shot transmission, both possible using real-world ECUs. Now we come to the impersonation stage of the attack. After a preceded ID frame, the accomplice and the attacker simultaneously impersonate a victim frame, raising an undetectable passive error frame, and also corrupting the voltage in the impersonated frame, matching the manipulated voltage fingerprint. Finally, the accomplice is needed in this stage for voltage corruption and transitioning to the error passive state. As a recap, what we did here was first pushing the attacker to the error passive state. This way we can achieve simultaneous transmission without raising detectable active error frames. Next, the attacker simultaneously transmits messages with the victim, corrupting its voltage. This way, the VIDS learns the corrupted voltage signature, which is a superposition of the attacker plus the victim as the victim's signature. Finally, the attacker and the accomplice inject malicious messages simultaneously. The VIDS will confuse this new superposition with the old learned superposition that is associated with the victim. We evaluate Duet with a test bed and 3 buses on our 2 vehicles, a 2011 experiment car 1 and a 2013 experiment car 2, with the experiment car 1 shown in the figure. Through a custom OBD connector, we have a laptop, an attacker ECU, an accomplice ECU, and 2 voltage fingerprinting defenses, one based on oscilloscope and one based on Arduino, connected to the vehicular CAN bus. We first look at the length of predictable payload on our test vehicles. We find that the predictable payload is quite high, with more than 80% of the messages having a predictable payload of at least 2 bytes across all buses. We look at the stealth of Duet during stage 1, and we look at the classification accuracy for distorted fingerprints for different levels of corruption, and find that Duet can conduct a low and slow APT-style attack by slowly corrupting the voltage values and staying in the yellow zone. We also look at the success rate of Duet against various predictable payload values. We find that even a small length of the predictable payload, such as 0.75 bytes, from the predictable control bits grant Duet a sizable success rate. We also evaluate Duet against various machine learning algorithms and find that Duet is effective against a variety of machine learning algorithms and is not specifically targeted against a specific algorithm. We move to a demo where, while in parking gear, we monitor the engine RPM of our experimental car on the dashboard and also in the CAM messages. Through a custom OBD connector, we have connected the duo of attacker and accomplice ECUs to the vehicle CAN bus. We also have an oscilloscope and a voltage IDS connected to the bus. The duo carry out the first stage of the attack during the training phase of voltage IDS, corrupting the voltage samples and manipulating the ECU fingerprint. The vehicle operates as normal during this stage. In the second stage of the attack, the duo impersonate the engine RPM messages, and the victim is suppressed using a suppression technique. Note that the voltage IDS does not raise an alarm in this stage, as the counter value remains below the threshold. To protect against Duet, we introduce RAID, a randomized identifier defense based on the key insight that Duet relies on periodic and predictable IDs. RAID converts the standard CAN frame into an extended CAN frame during the VIDS retraining mode. RAID randomizes ID by mapping the original ID-A field from the standard CAN frame into the extended CAN frame, and utilizing the 18-bit ID-B field for the padding. The receiving nodes can mask out the randomized padding, and they do not have to know the padding in advance. Note that RAID is designed for standard CAN frames, since safety-critical ECUs exclusively use them on high-speed CAN buses. However, RAID can be easily applied to extended CAN frame formats, allowing for a range of IDs to be chosen for randomization. In the voltage fingerprint manipulation stage of Duet, the attacker must predict the ID padding of a frame during simultaneous transmission. As victim manipulation requires multiple frames, it must predict the correct padding multiple times, which is extremely unlikely. With RAID applied, any incorrect prediction will result in a loss arbitration and transmission of two victim ID frames with distinct ID paddings, allowing RAID to prevent and detect the attack. Duet evades all existing VIDS by corrupting the voltage samples of only a few bits. RAID tackles this issue and randomizes the message ID, eliminating the root cause of the attack. We develop RAID as a complementary defense to existing IDSs, which can detect the attacks in prior literature. However, compared to the existing IDSs, which fail to detect the Duet attack, RAID not only detects but also prevents the attack, providing a lightweight and efficient complementary defense. In conclusion, we introduced Duet, an accomplice-assisted masquerade attack with two stages: voltage fingerprint manipulation and voltage fingerprint impersonation. In this attack, the accomplice-assisted attacker is able to efficiently and discreetly corrupt the voltage fingerprint. We also show a randomized ID dielecting defense, providing cheap and effective protection against Duet. Thank you.